It is time for solving rational inequalities. I hope that you agree that graphing rational functions is a bit more time-consuming than trying to graph the polynomial functions. The thing is, there is another way besides graphing, which we did for polynomial inequalities, that you can tackle rational inequalities. So I am going to teach you one and only one method to solve rational inequalities. If you would like another method, I can absolutely show it to you. It is, I'm going to say, worse, and it's worse because it's more time consuming, it's more unenvironmentally friendly because you'll be using way more paper. So I'm going to tackle it this way, but should you choose to want to learn another method, please let me know, or you can always go to the Grandmaster Google. So a rational inequality looks like this. So it's got the not, it doesn't have an equal sign. Instead, it's got either the greater than or equal to sign, a greater than sign, which is not here, a less than sign, or a less than or equal to sign. But it definitely has a rational. Now I've got some stars on these two, and I want you to know that these two are set up way better than the two that I didn't star. And the reason I say that is because the two that I starred have a 0 on one side of the inequality sign. So this one has a 1, which isn't ideal, and this one has a 5. The other two have zeros. So although a rational expression looks like a fraction and has a variable in the denominator, which we've looked at, we need to make sure that we have inequality signs, so the greater than, less than, greater than or equal to, less than or equal to. But the first step to solving using this approach is to write the inequality so that there is a single rational expression on the left side, I choose left, the left side of the inequality, and a 0 on the right. So that means this one's good, because here is a single rational, a single fraction on the left side with a 0 on the right. Here is a single rational expression with a 0 on the right. Here is a single rational expression on the left without a 0 on the right, so that's not great. And this one's even worse because it's got two rational expressions, or a split rational expression, with a non-zero on the right. So this one's the worst of the bunch. So this is your first step, and to be honest, your first step is usually the hardest. So I'm going to run down the steps, and unfortunately I'm going to have to blip back and forth between this slide and the next slide when we approach a question. So I'm just going to read through these. Summary of steps. Write the inequality so there is a single rational expression on the left side of the inequality and a 0 on the right side. Determine the changing points, and we'll talk about that, by setting the numerator equal to 0 and also setting the denominator equal to 0. When you get those answers, those are called the changing points, and you use the changing points to again separate the number line into intervals. So we're going to have to use the check method, which is actually way easier, way more basic math than it would be to graph or sketch. Number 4, select test values in each interval, so we've been through that, and substitute those values into the inequality. A, if the test value makes the inequality true, then the entire interval is a solution to the inequality. That would mean you color, and I'll write something in a few minutes, so give yourself some space. If the test value makes the inequality false, then the entire interval is not a solution, so you don't get to color, and I'll write something in a second. Then you get to choose between the high school set notation to give your therefore statement, or you get to choose between that or the university, which is interval notation. So we're going to go back and do those. So I am going to have 2 therefore statements so that I cover both methods of therefore statements. So I'll come back to this. If you at any time wanted to write these down from the video, my suggestion is pause, So I've left this here. I'm going to pause for a second. There. And there we go with the rest of it. Remember to leave a little bit of space for 4A and 4B so I can add some information in. So the next question, or the first question, is this one. And I am a happy camper, because even though it's got a very wordy set of instructions, it says what values make the following inequality true. You could be asked something as wordy as that, or you could be asked to solve. So they both mean the same thing. Now I am going to write down 3x over x minus 2 is less than or equal to 0. I'm happy about that. Hopefully you understand why, and it's because step 1 is done for us. We're super happy with this 0. So if I go back to step 1, it says write the inequality, so there is a single rational expression on the left side and a 0 on the right. Here is your single one rational expression on the left and a 0. If I go back to the second step, it says to determine the changing points by setting the numerator equal to 0 and setting the denominator equal to 0. So I'm about to find the changing points. You need to keep this stuff separate, just because I'm warning you. So I'm going to do the numerator here, and we'll shorten up some stuff in future questions. So the numerator is me taking 3x is equal to 0. I'm going to have to solve, so that means divide by 3, and get an answer of x equals 0. And totally separate, I then have to let the denominator equal 0. Pull the 2 over, we get that. So these two things right here are called the changing points. Next step. Use the changing points to separate the number line into intervals. So that's going to be pretty easy for me as long as you can do that numerically correctly. And then we're going to test values in each interval, so between the changing points, and we're going to substitute those back into the original inequality. So fortunately, because I wrote this is draggable, and then I can put it back. So first of all, my number line. And because it's a number line, and we're going to get to this in a second, so let me move it out of the way. I'll give you a sec to write it down in a minute. And instead of dragging that, I'll drag this. So you need to draw the number line with a ruler, because otherwise it's not a line. And we need to separate it. So I've got 0 and 2, so I'm going to put 0 here and 2 here. If 0 is not one of your numbers, do not put it on the line. I gave that tip during the polynomial inequalities. It's still true here. So eventually, we're going to have to pick numbers in these spaces, just like in polynomial inequalities. So I'm going to pick -1 out here, even though you could pick -23 if you wanted to. I'm going to pick 1 in here, even though you could pick 1.75. And I'm going to pick 3 out here, even though you could pick 47. So all you need to do is grab a number in those intervals and test it. Now, before I test it, I want to come to this thing, which says, remember, this is the eye on the prize. It says all numbers must be circled. So the first thing I'm going to do is I'm going to take these two numbers, the all, and I'm going to circle them. Now, it says numerator numbers get colored in when the symbol is one of those things. So I have to go back and I have to find the numerator number. So the numerator number that I got was 0. The denominator number was 2. So because I've got the less than or equal to, I have to color this in. And if I read my little blurb, it says denominator numbers never get colored in, and that is because you can never actually use 2 because that would create a 0 on the bottom. So this is saying that 0 is acceptable, but 0 is only acceptable on the top, so that's why you get to color in numerator numbers. So now that I've taken a little break from the question, I am going to put this here, and I'm going to do my check. And I'm going to do my check in red just for fun. Mix up my colors. So I'm going to check x equals -1, and I will put that in for all the x's. And we can show all our work, or some of it. And this says 1 is less than or equal to 0. And 1 is not less than or equal to 0. So that's false. So that is an example of 4b. So do not color interval. So your choice is either that you are going to do this or not. And because we ended up with false, it's not. So then I'm going to pick a number between 0 and 2, and I've pre-selected 1. So I'm telling you in my check area that I'm actually checking 1. Here's all my work. And that says -3 is less than or equal to 0, which is actually true. So I get to go up to the section where 1 resided, which is in between, and I get to color in that whole section. So if you had picked 1.75, you would not have -3 sitting here on the left, but you would have a true statement still. So that is an example of 4a, which is that you get to color the interval. And then, finally, we get to check our final spot. So this is a fairly laid-back kind of question, not many checks. And I check it in here. And again, just like polynomial, do not assume it alternates, even though a lot of times it does. So that's 9 over 1. So 9 is less than or equal to 0. I'm just totally copying this, and that's false, so I don't get to color. So I'm going to take all of this, I'm going to group it together, and I'm going to pull it down just so I have enough space to give you my 2 therefore statements. I knew that was going to happen. All right, time for the therefore statements. So we have to look at this picture and find out where we colored. So the first one I'm going to do is set notation, which starts the same way in rational inequalities as it does in polynomial inequalities, and then you get to tell me where you colored. So x, we had to color greater than or equal to 0, but we had to stay less than and not equal to 2. And there is your set notation therefore statement. Your interval notation statement, still, just like polynomial inequalities, makes you start xe, so x is an element of, and then we colored from 0 to 2. Now, this is a bit nitpicky, but I think easier than this version. We colored in 0, so you use the square bracket to indicate that. We do not color in 2, so you use the round bracket to indicate that. And now we are on to a second question. And here it is. And do you see why this one is, I can't dig out the happy face, this is an unhappy face. And the reason is because even though you have a single rational expression on the left side, you don't have a 0 on the right-hand side. So what we have to do is we have to fix this. So by fixing it, it means that you have to pull the 6 across the equal sign and subtract it. You leave the beak alone and you're leaving a 0 behind. So that solves half the problem. It solves the 0 problem, but it does not solve the problem that you don't have a single rational expression over here. You've got a rational and a little dangly piece, and that's not good enough. So you're going to have to get a common denominator between these two things, those two terms. And to do that, you need to remember rational variable expressions, adding and subtracting rational variable expressions from grade 11. And that's a tough concept. So I'm going to show you my way of dealing with this, and this will come up later in the course. I have this, even though it's called, getting a common denominator, I call this the 1, 2, 3 thing, and you might see why. It's not very imaginative. But the first step you do, which is why I call it 1, is you multiply those two pieces of information together. So that looks like this. And I'm going to be super literal in what I write down. Then 2 must be up to the left, and you multiply again. So that means we're going to take 1 and multiply it by 3x. Then, oops, that's 2. Then you multiply in this direction, and that's 3 out of 1, 2, 3. Super clever. You have to take x minus 2, and you don't multiply it by 6, you multiply it by negative 6. So that looks like this. And then you repeat the beak. And now you have to make this look as pretty as you possibly can. So 1 times 3x is 3x. Negative 6 times x is negative 6x. Negative 6 times negative 2 is positive 12. All over 1 times anything is itself. Same beak, same 0. Then we can collect like terms. So 3x minus 6x is negative 3x plus 12 over x minus 2 is greater than 0. So I am now going to take this, which is exactly how it's supposed to be set up according to step number 1. That is single rational expression on the left, a 0 on the right. So I'm good to go. And this is something you can check in later, or any version up above, including the original typewritten version. But before we do any checking, we need the numbers for our number line. We need those changing points. So I'm going to take the numerator, there's my short form. Again, super inventive. Make it equal 0. And solve. And so far, we're doing pretty well. I'm keeping it kind of simple because they're all linear, as in they're all degree 1 statements, both on the numerator and the denominator. So we get 4. And then the denominator is x minus 2 equals 0, so x is equal to 2. So I'm very popular. I am going to separate my line using 4, I found it first, and 2. Not that it matters which one you put down. And then I'm going back to my little blue hint from before. which says I have to circle all the numbers. If I have the or equal to signs, I get to color in the numerator, and I never color in the denominator. Well, for this particular question, I didn't have an or equal to sign. I just had a plain old greater than sign. So that means there's no coloring anywhere. And now I need to check. And just to spruce up my color, I'm going to pick red again. So I'm going to pick a number out to the left of number 2. So I could pick 1. I'm picking 0 because 0 is the easiest number to work with. And I'm putting it into that typed written fraction off to the side. And I do a little bit of BEDMAS and figure out whether this is true or false. So 0 over negative 2 is greater than 6. 0 is greater than 6. No, that's false. So now I'm going to check a number in between. I'm not going to use a decimal if I don't have to, so I choose 3. So it's 9 over 1, and 9 over 1 is 9. 9 is greater than 6, so that's true, and I get to color. And then finally, I need to pick a number that is bigger than 4, so out in this space, so I'm going to pick 5. So 15 over 3 is greater than 6. 15 divided by 3 is pretty. 5 is greater than 6. No, it's not, so I don't get to color. So there's a picture of what I have to write the therefore statement about. And I'm going to put my therefore statements right beside my number line. So first of all, set notation. X such that X is an element of the real numbers, so they're like normal numbers. And I colored between but not equal to the numbers 2 and 4. When I get to interval notation, I have to start XE, and or X is an element of, and I still colored from 2 up to 4, but I didn't include either one of them, so that's why the or equal to's are gone. But you don't want this to go missing because that says 2 comma 4, so 2 to the right, 4 up, and that's not actually what you mean. You mean every number on the x's between 2 and 4. So that means if you take a look at this statement right here, only numbers between and not equal to 2 and 4 will make this a true statement. Everything that's 2 and smaller, or 4 and bigger, will make this a false statement. So you're just giving a list, a funny looking list, of answers that'll work for the inequality. So we have one last question to do, and then a question that I'm not finishing. So first of all, this guy. Actually, I'm going to take a little break because my hand's cramping. Okay, pause over. So, this is not set up perfectly because I don't have a 0 and I'm not going to end up having a single rational expression sitting on the left. So I still have to go through the same steps, so I still have to take something over to one side of the inequality sign. So what I'm going to do is I'm going to treat this like it's in a little bracket. And if that's in a little bracket, then when I pull it over, that bracket will have a subtraction sign instead of the original invisible positive sign. And then I'll have the beak with a 0. I'm going to put my 1 down because I really like the visual, and then I'm going to do my 1, 2, 3 thing, which is essentially what you do in grade 11 math with rational variable expressions, which are just fractions. So can you get number fractions with common denominators or not? And then can you translate it to this? It's actually pretty tough. So we're going to have to multiply this by 1 and this by 1 and this by x and this by x. So what happens is if I ask you to do the 1, 2, 3 thing, I get 1 times x, which is what that would be and that would be. Then I would have to go up to the left first. So that is 1 times x minus 8, which is exactly what that would be. Let's make my bracket look prettier. And then I would have to do the third step, which is to take x and multiply it by 3 minus x, which is exactly what I said here. And you have to have that subtraction sign in between. So if that's an addition, that's an addition. If this is a subtraction, you keep it a subtraction. Beak 0. I am going to erase some of my clutter. All right, so time to multiply this out and collect like terms. So 1 times x, 1 times negative 8, negative 3 times x, negative x times negative x, over 1 times x is x. So x squared, not impressed with that. 1 minus 3 is negative 2x minus 8 over x is less than or equal to 0. So my numerator is x squared minus 2x minus 8, set it equal to 0. Give myself some space. And I'm really hoping this is factorable and not me having to use the quadratic formula. So can I find two numbers that multiply to be 8 that can make negative 2? This is a simple trinomial, and I can. So 4 times 2 is 8. Negative 4 times positive 2 is negative 8 and negative 2. And green pen, just to annoy some of you. And I end up with x equals positive 4, x equals negative 2, and I can move on to the denominator. And notice how I'm still being very clear about what I'm doing. And that one doesn't need solving. Yay! So, number line. Pen. 0. I know I can put a circle around that. Negative 2 would be over here somewhere. I know I can put a circle around that. And 4 would be over here somewhere. No need to go to scale. I can put a circle around that. And I need to color in my numerator numbers. So I need to color in negative 2 and positive 4, but not 0 because 0 is a denominator number and you never get to color those in. So time for my red check. So I have to check a number outside of negative 2, so I'm going to pick negative 3. And I am not checking in this monstrosity. I am going to check in this monstrosity. Now, here's another thing about this thing. and I will write it down and then scale it back a little bit so I have some space. You could either use this, or you could use the original equation, or you could use the fact that we had a factored version of this, and I'll show you why this is a good thing in a minute. Let me just group this together. And make it a bit tinier. So I'm just going to haul that along with me. I think that's a good spot. So, -3 squared minus 2 times -3 minus 8 over -3. So that's 9 plus 6 minus 8 over -3. So that's 9 minus 8 is, 15 minus 8 is 7 over -3, and I am trying to figure out if that's less than or equal to 0. And because that's negative, negatives are less than or equal to 0. Yes, they are. It's true. I get to color in the -3 space. Now I'm moving on to a number between -2 and 0. Now I can't do what I'm about to do with the top one. I can only do it with the bottom one because the bottom one is factored, and factored means it's a combination of multiplying and, in this case, dividing. And we have rules for integers with multiplying and dividing that don't exist for the adding and subtracting questions. So we can go back and do that little clever plus minus thing, which is why it's worth taking a look at this. So -1 minus 4 is -5. -1 plus 2 is +1. -1 on its own is negative. Two negatives and a positive when you're multiplying and dividing is a positive. So you have to ask yourself, are positives less than or equal to 0? And that is a false statement. Now, having said all this, because you have many choices of where you can sub in for your check, I mean, you could even pick this one. You need to tell me what you're checking in so that I know what's going on. Next check, and I'm going to still do this one, is any number between 0 and 4. So I'm going to pick 1. 1 minus 4, -3. 1 plus 2, +3. 1, positive. So this is a negative answer because we have one negative. Negatives are in fact less than or equal to 0. So that is true, and I get to color. So this little plus minus dealie, you are not allowed to do that here, even though this is all multiplying and dividing, and that's because you're not comparing to 0, and 0 is, I've heard it been called the portal between the positives and the negatives. So because you're not comparing to 0, which separates your negative numbers from your positive numbers, you can't do the check in the original with any short form whatsoever. So for this one, I'm going to go back to the original for 5. So I'm telling you, I'm putting it in x equals 5, or x equals 5, and I'm going to put it in for all the x's. So you have a choice about what you want to do. You just have to communicate your choice. And notice how I'm dropping some things, like the beak, until the very end. 25 minus 10 minus 8 over 5. 15 minus 8 is 7 over 5 is less than or equal to 0. This is a positive value. Positive values are not less than or equal to 0, so that's a false. So I need a little bit of room, so I'm going to pull this stuff down here, which is why color coding for me works so well. And this is the spot I'm going to put my therefore statement. So, set notation. You need way more room than that. I've got 2 spaces this time. So this is x is less than or equal to -2 or (0 to 4), x is less than or equal to 4 and greater than but not equal to 0, end the set. So these little squiggly things are called set brackets. I'm hoping I can fit interval notation in here. If not, I'll move it down in a sec. I need the x as an element of. I am coloring from -infinity up to -2, including it. Here's your other symbol for or, so they can be used interchangeably. I'm coloring from 0 to 4. I included 4. I did not include 0. Your choice. I accept both. Little break before we take a look at this one, which I'm not going to actually completely solve. I'm just going to set it up to solve because I want to make sure you know how to get a common denominator, step 1, with a 0 on one side, a single rational expression on the other. I want you to know how to do it with something as complicated as this. So give my hand a rest and I will be right back. Okay, I did a couple little hand exercises and we're good to go. Oh, I'm going to cough. I'll be back again. All this talking is making my throat scratchy. All right, step 1. Oops, huge step. Especially for this question. Getting that 0 is easy. So it's almost like this fraction's in a bracket, but I'm not wasting the pen strokes to put it on there. Leave the beak alone. I've left nothing behind, so I need a 0. So now I can do the 1, 2, 3 thing, and this is complicated or time-consuming. 1. Multiply those together. 2 to the left. And it doesn't matter if you put 3x plus 1 first or last, as long as you include both brackets. Minus sign. 3. Doesn't matter if you put x minus first, x minus 3 first or last, as long as you have both those brackets. Beak 0. So we have to multiply out this numerator and collect like terms. This is going to take a bit of work. I am not going to multiply out the denominator, and that's because I'm supposed to let my denominator equal 0, and that would mean I would FOIL it out, and then I would have to factor it, and it would come back to this again. So I leave the denominator. Your numerator cannot be left. Now I'm going to totally cheat. There are people who would absolutely dislike me for this. I'm going to totally cheat and just deal with the numerator. I'm going to put it here, and I'm going to put it here in green. So 3x multiplied by x, 3x squared. 3x times 4, 12x. 1 times x, 1x. 1 times 4, 4. X times 2x, 2x squared. X times -5, -5x. -3 times 2x, -6x. -3 times -5, +15. And a lot of people are going to put this little minus sign down here, and you're going to be wrong. And the reason is because that means only this term is negative. You can either change all the signs if your brain power is great enough for that, which mine isn't. So the alternative is to wrap it in a bracket, and then in the next line, I'm going to collect a little like terms here as well. In the next line, run your negative through this bracket. So -1 times all of the terms. And I tend not to skip that step because I don't want to make any mistakes. And as long as I see this somewhere, the margin, something like that, I can tell whether you have the right answer and whether you went through the right steps. So 3x squared minus 2x squared is x squared. 13 plus 5 is 18. 18 plus 6 is 24. X. Sorry, just checking something. And 4 minus 15 is negative 11. All of this, so see how I was quite smart to save myself some pen strokes. I have this, and then greater than 0. So I would then move on to numerator, denominator. You can do it sideways or on the up and down. I try to make sure I use my paper nicely. So the reason I don't want to continue this is because that was the hardest part. So this one I can do really quickly. I'm going to even avoid the green writing just to show off. There we go. But this one is a simple trinomial, so I need to find two numbers that multiply to be 11 that at the same time add or subtract to be 24, and that doesn't happen. So this one will need the quadratic formula, which just means you end up with two decimals. And then you can put negative 4 and 3 and your two decimals on here, do your check, etc. So it's not a big deal to finish this. The big deal was doing all of this stuff. So I do not have a slide in this document for the questions. There is a set of questions in your booklet, and you can do as much or as little to prepare for what we need in class. So I'm just going to move this along, and you can pause wherever you need to if you're trying to write and watch at the same time, which would not be my preference because I am not a good multitasker. Done. Catch you next time with a little bit of trigonometry.